Welcome to our video series on generative AI. I'm Kevin Boyd, the CIO at the University of Chicago, and I'm very pleased to welcome Professor Michael Maire from the University of Chicago Computer Science Department for a discussion on generative AI models.
Thank you, Kevin.
Thank you. Professor, let's start with a little bit of generative AI generally. So there's obviously a lot of buzz around generative AI. How do some of our current models differ from some of the past models, let's say more than 2 years ago?
Well, I think what we're seeing here is a new class of generative AI models that give additional capabilities in terms of actually being able to synthesize examples of data that resemble a collection of training data, but are distinct from any individual training examples. So we have new ability to synthesize in a way that generalizes and actually yields some understanding of the domain. And another aspect of these generative models that is exciting is that we can think about generation as a objective for learning, and if we probe the representations and latent structure that these models produce, we can actually use those models for downstream tasks with a little bit of fine-tuning. So the generative models actually seem to be learning about the latent structure of data in the training sets that they consume. And so learning to generate might be a widely applicable a task for learning.
Interesting. Okay, so today we're talking about some of the underpinnings of how these tools work. And I think many of us have experimented with tools like ChatGPT or Bard or Gemini. But I'd like to understand a little bit more about what's going on under the covers. So let's say I go to one of these tools and I say, write me a poem in the style of Robert Frost about an apple tree. Mm-hmm. What's happening under the covers with the transformer model to actually produce results?
Sure. So the transformer model is is taking a piece of input text and trying to predict the next most likely word in the sequence. And so in order to do this, what makes a transformer architecture a little bit distinctive from previous architectures is that it's looking at a context of the preceding words, and it is trying to compute and fetch a mixture of those words that are most relevant to the next output. And so internally, it is building some representation of each of the previous input words, and it is then kind of dynamically attending to the pieces of input text that are most relevant for the next prediction. So there's some additional computational cost in looking at this long history. But that's also giving it lots of expressive power in terms of performing the prediction task.
Interesting. So it's looking at the training data that it has, and then it's making predictions about what words should go together to produce the poem I'm asking it to create.
It's looking at the specific training instance that you've prompted it with. So you might prompt it with discussion with a sentence like create a poem about a certain subject. And so it's looking at that instruction to figure out what to do next. The entirety of the training set comes in terms of the parameters of the model itself. And so those parameters are the weights that determine how it is figuring out which pieces of your previous input are most important. So the entirety of the training set is kind of distilled into the internal parameters of the model, and then that behavior affects what it does on any individual input.
Okay, so that's very helpful. So let's talk about another type of model. So diffusion models, which I think often is used like with image generation, for example. So let's say I ask the model to create an image for me with a dog in a spacesuit on the moon. Mm-hmm. What's happening with a diffusion model under the covers in that case?
Sure. I think of diffusion as a kind of training paradigm. So in terms of the underlying architecture of the diffusion model, I might plug in a transformer there. I might plug in a convolutional neural network or some combination of them. The training paradigm of diffusion is that the task I set up the model in terms of how I'm going to set all the parameters of the model. I'm going to optimize the parameters of the model for the task of taking as input a mixture of a data example and some noise, and separating the two as an output task. So I want to either recover the denoised data example without any noise present, or recover the noise that I added. Those are kind of equivalent. And if I vary over my training regime, kind of all possible mixtures of data with any level of noise, I vary the noise level, then I'll have a model that kind of learns from any mixture of data and noise how to map back onto the set of training data or the data manifold. And then I can actually use this in a synthesis application by feeding in a pure noise signal, and then having the model map along some trajectory back to the data manifold. And it turns out that we not just get a model that memorizes the data, but that actually generalizes, and so will synthesize new examples of never before seen items, but that resemble the original input domain.
And just a little clarification, when you talk about introducing noise into the model, what does that mean?
So one example is I use a random number generator. I generate Gaussian random numbers, and I create a entity that is the same dimensionality as my data item, and then I linearly interpolate a mixture of that data item and that noise. So I'm really just mixing in some random perturbation to every component of the data.
Interesting. Okay. That's helpful. I think I have a little better understanding of how these models work under the covers to create what I'm asking them to do. So let me close out with a general question. Let me ask you to peer into the crystal ball a little bit. Looking ahead, how do you see the fields of, how do you see the generative models evolving? Where do you think we're going? Are there some exciting trends or emerging technologies?
So maybe I'll continue my thought on the last answer, which is I think there might be opportunity here in combining these very general purpose neural network components that we have right now, like transformers or CNNs, with some amount of additional structure in the architecture of models, where that additional structure is related to the problem domain. And the hope is that it provides some prior or constraints on what is learned, such that you get potentially additional data efficiency out of these models. So you might learn faster with a smaller amount of data. And you might get some additional structure that emerges as a result of training these models, or have some handle on how to interpret that structure. So I think there is a big question with neural networks, and this extends to generative models now, on how to interpret what they're doing internally. And so I think and hope that there might be ways in which we can attack this problem through things like model architecture or other aspects of the model design that still give us these wide capabilities for generation and synthesis, but also give us additional insight into how these models are internally computing on data.
Interesting. All right. Well, Professor Michael Maire, thank you so much for joining me today. I really appreciate you being here.
Thank you, Kevin.
And thank you for joining us for our series on generative AI. Today's segment was on generative AI models. I hope you will join us for additional segments in the series. I'm Kevin Boyd, the CIO at the University of Chicago. Thank you.